Hello, my name is Tony Afshari, and I'm Senior Director of Product Management at Plyops. Happy to be here. And today we wanted to tell you about what hardware acceleration will do for improving infrastructure, and specifically how to multiply an IT infrastructure investment with the power of X. So a little bit about Plyops. Our mission is to massively accelerate performance and dramatically lower infrastructure costs for relational databases, NoSQL, in-memory databases, analytics, AI, ML, 5G, IoT, and other data-intensive applications. We're very proud of our team. The core capability of our team is around the fabric of people that we have. We are based in Israel with worldwide business headquarters in the US and offices all around the world. And we have the most amazing experts in databases, flash storage, and semiconductor from industry leaders, including Samsung, Intel, Kioxia, Amazon, Microsoft, and several other worthy companies. Our strategic investors include Intel, NVIDIA, SoftBank, WD, and Xilinx, soon to be AMD. So we are in a very unique position to have all three vendors, including Intel, AMD, and NVIDIA investing in us. Many accolades from industry, but let's talk about a little bit about the problem itself. So if you look at the growth of SSD drives in the IT world and the infrastructure, you see something north of 6x, since 2015 to 2020. That's pretty good and pretty massive, but we really haven't seen what's coming our way. And that's a 40x improvement for the deployment expansion with SSDs, especially with NVMe SSDs going all the way to 2030. And well, this presents a problem, and we like to tell you a little bit more about that, especially around building efficient infrastructure. If you look at what NVMe SSDs are doing and the deployment of them versus rotational media or other kinds of SSDs and the rate that the NVMe SSDs are getting deployed, you see clearly a lag of what CPUs can handle and where CPUs will run out of juice, handling this awesome power of NVMe that has come our way. And the current problem, or the yesterday's solution for this, was to throw more CPUs, more servers, more infrastructure cost at this. So all translating to not being able to efficiently maximize and use your infrastructure. To give you a little bit more detail, there are three areas that specifically come to mind which are considered challenges to broad SSD and broad NVMe SSD adoption. One is server architectures. As SSDs are now 1,000 times faster than HDDs used to be, the server architectures have not advanced and kept up with that. Amplification of data. This is a major problem. Software and applications or solutions that use SSDs amplify reads, writes up to 100x, and store data up to 6x, crushing storage and network efficiency. And one other item that is very critical is system reliability. Traditional RAID is rarely used with NVMe SSDs due to the huge performance penalty, and it requires costly workaround. We like to zoom in on this because we think by moving storage management and storage functions into an accelerated model away from CPU, we can overcome all of these and build a very efficient infrastructure. If you look at, how sort of IT world and infrastructure looked like in the past, we used to call it, we like to call it the compute-centric. That was the yesterday's era. And today it becomes a data-centric era. And having said that, well, the compute-centric was all around what the CPU can do. CPU managed everything from traffic control, from applications, and from storage management. And because in that mix of storage, you had both rotational media and SSDs, or even performance tier of compute, there was a lot of latency in the table left on the table that allowed for some hiding of some of these inefficiencies of CPU. With today's world, and given that everything that is now added on top of the cloud with the edge, with the 5G, you have seen a trend and reality that CPU is already offloading things to adjacent accelerators. In this case, we saw how AI and ML started running on the GPUs, and they even have their own dedicated processors. And it's the same continuation, now moving things, storage functions, to an accelerator, to a hardware accelerator, such as Plyops XDP. And the benefits of that are around improvements to performance, improvements to reliability, improvement to capacity, efficiency, and better usage of capacity, and improvement to efficiency of using SSDs and the types of SSDs. And this is going to continue. We see this offload and this hardware acceleration moving into taking even more of a chunk away from the CPU, with DPUs taking full control over traffic-related items and security-related items. There's a panel that Plyops is participating on as well around DPUs at this SDC show. And we see a great combination of using a DPU and a Plyops XDP data accelerators to even further provide better isolation, better security, better scaling. Now, what would the solution like this look like? Well, in the case of Plyops, it's a half-white, half-length PCIe card that easily fits in any server. From a reliability perspective, from a performance perspective, we see anywhere from 3 to 15x improvement in application performance, depending on what kind of application that is and what the interface is like. And the second pillar is all about reliability. Drive fail protection is a feature that Plyops XDP offers, and it allows you to be able to recover from drive failures, but be able to perform even better than RAID 0, which is the fastest striping algorithm there is available, and be able to rebuild faster. We offer a great amount of flexibility and configuration to the user, but also with efficiency and around capacity, because you're writing a lot less to the drive, and you're writing a lot more efficiently and in a more compact way. There's more space left on the drive, and more importantly, let's talk about the next one. When it comes to efficiency, if you are writing very efficiently to the drive, then you can add more capacity to the drive. You can fill it up more. You can feel more comfortable to put more data on that drive. But more importantly, you can also use more economically oriented drives like QLC or data center grade TLC, and even ZNS drives, and do this very efficiently, very transparently, not to have to change any software. To give you an even more in-depth understanding of how does this exactly work? Well, at the core of it, a solution like Plyops Extreme Data Processor combines multiple key data and storage technologies into one device that together multiply their benefit. If you notice, the core of the product is around a hardware-based storage engine that uses breakthrough data structures and algorithms to deliver what's equivalent of what 1,000 Xeon, hundreds of Xeon Gold cores can do, thereby eliminating the inefficiencies of software-based solutions. The device presents itself as very seamlessly to the application. The interface, it's either a standard block device or further integration into application with a KV library, with the key value library. Applications that are using RocksDB, for example, as a storage engine, it becomes a very easy integration with our version of RocksDB that is suited and tuned for the Plyops accelerator, hardware accelerator. And so depending on which route and what application and what kind of infrastructure the customers are building, both of these are available. Once the data is handed, it comes into our domain as in form of blocks, it goes through a very strong compression engine. These are multiple compression engines available that are on our hardware. And then at that point, data now is in an object world, and data becomes variable size objects. It can vary from few bytes to hundreds of bytes and even bigger. And so at that point, our library and our database and our key value engine manages those variable size objects, creates these very large, nice, flash aligned sequential writes to the drive. So it's never written in a random fashion. It's always sequential. And again, think of it as more like an LSM algorithm, but it's running on gates. There are no cores involved here, and it does the same kinds of operations such as merging, packing, sorting, indexing, and garbage collection all at once, all in hardware, all in wire speed. So once data is getting ready to be laid out on flash in this very effective and efficient way, then it's also an advantage to be able to provide data protection, because with our data failure protection, we have designed an algorithm that is for NVMe drives, that is for flash. So, and it only touches the data that it needs to add parity to, and it only touches the data that it needs to be rebuilt. So with that reduction of data and knowing exactly what to rebuild and what to add parity to, you are doing the operations a lot faster. And because there's never a read modified write, like traditional RAID solutions, RAID 5 solutions, you deliver a very effective data protection system that right now it's probably the best NVMe data protection algorithm there is out in the market. Same with encryption. Again, reducing what needs to be encrypted and using effective ways to do that in wire speed all at once. The solution itself will present it in a Linux environment, will present itself as a block device, same with Windows. And that block device, again, the application will require no change to it. It's just we'll be seeing another storage device in the OS, and we'll be directing its IO to that device. The nice thing about this solution is that, again, the storage is not abstracted by the Plyops controller. The storage is sitting adjacent to it, whether it's physical SSD sitting on the same server, or there could be an EBOD or a JBOD somewhere else. or it could be a network drive, or a NVMe over Fabric drive, or driver sitting, allowing storage to sit outside of the server. But all of this, again, is very transparent, and we don't get in the way of managing that SSD. Those SSDs can be QLC, TLC, or Optane, and they are, again, accessible by the host. They can be managed by the host. You can still read all the smart attributes for those drives directly for out-of-band management, etc. To give you a feel for the kinds of gains you'll see with a solution like this, these are not meant to be compared together. This is just showing the multiplications of improvement with the application scaling. The lighter blue is for native key value interface, and the bigger blue, or the darker blue, is for block. So RocksDB, in this case, it's comparing RocksDB running on software only without the hardware acceleration, and showing how much better the performance of RocksDB will be once it's in Plyops domain. With QLC, it shows how much gain you get when using QLC with a solution like Plyops versus QLC on its own. Redis, significant improvement there by being able to extend data set size over beyond what DRAM can contain, but yet suffer no delay and latency, and be able to deliver as a solution as powerful as DRAM. And then with traditional databases like MySQL, like Maria. But as we talked about, performance is not the only pillar that the solution offers. It's a combination of performance, data protection, capacity, and efficiency. And what that translates to at the end of the day is significant TCO savings. As you can see, we have some examples that will show you. In the case of RocksDB, QLC, and Redis, the savings, the TCO savings, are north of 75%, and just as attractive it is for MySQL, MariaDB, and Mongo, north of 50%. We talked about data amplification. These are some measurements that we took with, on the left, with traditional databases that use storage engines like B+tree, like MariaDB, like MySQL. And you can see how we have read amp and write amp and storage amp in multiple X's here. This is a log algorithm, a logarithmic algorithm, scale, sorry. And if you move to something newer, like an LSM algorithm database engine, such as what some of the newer solutions like Kafka or Spark, etc., use, or Roxandra. Again, they do a very good job improving some things. So some of those were designed specifically around Flash, not to burn Flash and not to put too much data on Flash. So they've done a good job with being to do to manage the storage amp, but they fail miserably when it comes to read amp and write amp. So it's a hard thing to balance if you're running everything on the CPU, on the host, on the software, because it's hard to balance these three. But with a solution like Plyops XDP, you can manage all three of those and reduce read amp, reduce write amp, and reduce storage amp. Specifically around drive fail protection, this is a feature that is very critical to data center customers. We allow, this solution will allow full uptime with multiple single drive failures, full performance with data protection. So you can have multiple drives in this array fail in a row and still recover from that, which is significant. So we'll use a couple of examples for that. You can have what we call virtual hot capacity, which will reserve existing space across the array of drives and allow for the event of a second failure to be able to use that space as a spare drive. All data and metadata is protected against sudden power failure using onboard NVRAM. And as we talked about, because rebuild is applied to only the data that it needs to be rebuilt versus traditional RAID solutions out there, the recovery and is extremely fast, and only data that is stored will be rebuilt. And then automatic rebuild. This is, again, a flexibility of the system. We have different operators, IT operators. There are some that choose not to even start a rebuild. They rather send a tech to replace the drive. There are ones that want to say, I don't want to rebuild until certain hours during the day. I know that I can recover from a second drive fail, so I feel very comfortable with the solution. I want to do it later. And then at that time, even, they can specify what's their rebuild time, because they can be very aggressive or they can take their time. So these flexibilities are what really customers like. A demo, and I don't want to run the video here, but I've taken some snapshots of it. So what we did is we compared two identical servers, one with Plyops XTP, one without, just software. So the yellow line basically is the same drives and the same server, we've applied a RAID 0 algorithm to those, so they're the fastest way you can get data out of drives. And of course, there's no drive fail protection there. There's no, if a drive fails in that model, the whole array goes down. And then with Plyops, we have drive fail protection enabled. In this case, we also enabled VHC, virtual hot capacity. So we added another drive to have enough capacity to not only have enough space for parity, but have enough space for a spare. The algorithm is a distributed RAID, meaning you don't have a dedicated drive that is holding the parity or a dedicated drive that is hot spare. All of that is managed across the array of drives. And so we collected the data from IOStat. So this is a Linux system. We were running IOStat and we were collecting the data. So we were looking at system throughput, and we were running FIO, essentially orchestrated run across the two servers. So push a button, the same exact FIO scripts run on both servers. Data gets collected. We used Grafana in this case to be able to display what happens. So on the top, these are writes only. On the bottom is reads only. So that's the way we graphed it with, or charted it with Grafana. As you can see, even with drive fail protection enabled with Plyops, we saw a 4x improvement in throughput based on what the system is seeing, based on what IOStat is reporting. The reads only are also faster. And the reason in this case is we're actually delivering more than what the drive specs indicate to the host. And the reason is because we're decompressing the data on the way back, we're delivering more bits to the host. In a mixed read-write environment, so this is a 70-30% mix, we still get significant improvement. So write intensive, read intensive, and mixed read-write. Next, we move to demoing drive fail protection. So as you can see here, this shows times. This is 17 hours, 10 minutes, 17 hours, 20 minutes. So each one of these are 10-minute ticks, essentially. And we have instrumented Grafana to show exactly how we're failing the drive and what's the rebuild progress. So you can see that we have failed the drive, and we've entered a rebuild mode to be able to go back to a full RAID, protected RAID 5 solution with DFB. And even during the worst stress on the system for a drive rebuild, we are seeing still 2 times faster throughput on reads, and same with reads, on writes versus, and same with reads. And this goes all the way through. As you can see, we where I'm pointing is about 18 hours and 50 minutes. We are back to full array. We have used our VHC volume to be able to go fully, completely back to a RAID 5 setup or a full drive fail protection setup. And during this whole time, we saw that the rebuild with that much data took very, very quickly. So we went from essentially 17 hours and 20 minutes to 18 hours and 50 minutes. Another interesting data point that we recorded was around write amp. So we have the capability of literally, these are some drives like Samsung and Intel. There's a way to collect what the drive is seeing as far as the number of bytes written to the drive. So in this case, we wrote a very simple formula that was charted using Sysbin. Using IOStat and using Grafana, that shows how many bytes were written from an IOStat's perspective to the drive, and what did drive record as far as number of bytes written. So that's what this is. As you can see, the case of RAID 0, software RAID 0, the write amp ended up being somewhere north of 5 times, greater than 5. But in the case of Plyops XDP, the write amp ended up being less than 1. So this all is around that efficiency that we talked about, how you can manage your drives, manage the max performance and latency, best latency you can get out of them, how you can feel very comfortable by putting more data on there and building, feeling more comfortable with filling it up, and then expecting a very consistent performance over time from that array. All of that helps customers build better infrastructures. There are 4 cases that I like to mention. These are some of the prominent ones. You're seeing people deploy, customers deploy Plyops XDP. Again, similar to other hardware accelerator solutions that are using that are offloading the storage functions, but in our case, it's very, very transparent solution, addresses many of the inefficiencies that there are out there. One is around disaggregating infrastructure. Cloud operators are facing a deluge of data and are looking to scale and keep costs down. Plyops is helping them build reliable storage systems. These systems utilize distributed file systems and offer everything that a high-end, super expensive all flash array will do, yet they're built with commodity servers and open source software. So, and the second case, the empowering the application server, this is, again, they're building reliable database servers with all flash storage to host more instances and improve their transaction costs. In the HPC world, and you'll see us demo some of these at the Supercompute this year, is lots of compute elements out there, very, very hungry for CPU cycles. So storage, when it's needed, it needs to be very efficient and keep those machines, make sure those machines are not starving. And so we're helping build very efficient, high IO storage servers. These are for the most part, are key value based. So the applications are using something like a RocksDB as a storage engine. And because data is in different sizes and objects, it's a lot easier to manage that with a key value interface. And that's exactly the kinds of things that the Plyops card shines. Another interesting example that I like to bring up is we're seeing this become very popular, and that's database backup offloading. So this is very important around the big data applications where for backup, these operators are using to use less and less CPU cycles to do the backup. So if they can offload compression and offload backup functions to a solution that can do it better than CPU, it's something that they're looking for, and that's where a few use cases that we're seeing people deploy Plyops with. Let's talk about that case where people are building disaggregated storage. This is storage that can scale independent of compute, that can host anything, that can grow and sort of, be prepared to address those key crazy calendar dates for these public cloud and web scalers. So the structure looks something like something similar to what Gluster does. So it consists of a few different servers, a group of servers. They have erasure coding built into them. So it could be like a 10+2 configuration. And that works really well because you can recover from a drive fail, and you can also recover from a server failure. And the way the drive fail scheme works is each SSD in that, from each server is grouped into a brick. And so the brick includes an SSD from each one of these servers. If one of these SSDs fails, there's a rebuild that takes place across that cluster, if you want to call it. And well, there's a cost associated with that. You don't want to make that too heavy or too dense, because the rebuild time is more, and then the failure domain becomes more critical. So what the operators are doing is they're putting a solution, they're putting Plyops XDP in the mix, and instead of a single SSD in this case, they're putting multiple SSDs. For this generation of the product, they're putting in about 192 terabytes worth of SSDs behind a single Plyops card and Plyops XDP card. And with that, now you get many different things. You get much denser storage. You can use solutions like QLC. That's what a few of these guys are using. And what that will allow to get economies of QLC with performance of TLC, yet with data protection. And so the opportunity to make these arrays denser, now it's more reasonable, just because there's a lot more reliability and performance consistency when Plyops XDP is added to the mix. So you get an improved QoS with CPU and network east-west traffic. You can use QLC SSDs without performance hits. You can use larger and more reliable clusters, and this all translates to capacity expansion by 43%. Zero downtime. If it's related to drive failure, you have essentially eliminated that, and reduced the cost by 36%. Another example is a SaaS provider. In this case, it goes back to the density of the system and how much, if you're offering software as a solution and database as a solution, well, how much can you host more, or how much much more can you get from your infrastructure? So what we're comparing here is the case without Plyops and what happened when the Plyops is added to the mix. Because of, again, concerns about capacity, performance, failure domain, The customers were, in this example, were using two 15 terabyte SSDs, and each one of these, this is a cluster that is running something like MariaDB, and let's say it was about 15 user instances on the left. It was about 41 terabyte usable, a RAID 0 setup, 600 server failures per year. This is just looking at MTBF of those SSD drives. And then moving in with Plyops, you have the ability to do exactly the same thing and more with a single server, now offering 8 terabyte SSDs, being able to host 20 user instances per server, and then improve the capacity to 66 terabytes of usable capacity, and add drive fail protection, which will reduce the drive failures due to server failures due to drive function, and rebuild across that to 0. So this translates to 50% lower cost, 600 fewer server failures, 33% more users, and 66% more usable capacity. And the final example I wanted to show you is around Redis and in-memory databases. As you know, the footprint and how much data set, how big data set is you can use for a solution on Redis is around how much RAM you can have in a server. So if you're building a cluster of, let's say, 6 terabyte DRAM based system, you essentially need 10 servers. And if you can, again, we use the Mentier to measure some performance here, and we saw about 920,000 IOPS and about 1 millisecond in 4.9 latency with the system on the left. What happens is when you add XTP to the mix, now you can simply expand your data set size by being able to spill over to NVMe drives or even Optane, and significantly increase your data set size, yet be able to handle the performance of what's expected on the left. So the translation of this is much better efficiency in infrastructure and lower cost. So we went from 10 Redis instances on the left to 1 Redis on with Plyops, and we saw again about 910 K IOPS, so not that much different than what was on the left, and roughly the same latency on the 4.9s, 1.11 milliseconds. So this allowed us to do a lot more with a lot less. So this allowed us to deploy in-memory performance for much larger data sets at a very low cost. In summary, I like to tell you that the era of storage hardware acceleration is here. This is a trend that has started with GPUs and with AI and ML accelerated machines. Integration is very seamless. We talked about this. I showed you examples of applications absolutely do not need to change for this. This translates very easily and transparently to them. Drive failure protection for NVMe SSD is a game changer. We believe this solution is the best there is in the market. And QLC and ZNS SSDs are now equal or better than TLC. So this will empower QLCs to have to perform as good as TLC drives. So bringing that economy of QLC to the data centers and saving massively in infrastructure costs. Again, I thank you for participating in this session. We will be on the panel with the DPU group, and you can go to plyops.com to get more information about us. You can request a demo, and we are very excited because we're commercially available now through distributors as well, and we would love to help you build better infrastructures. Thank you so much.